Hi, my name is Natasha, and this presentation will be about the project Mat2Bat, which Bailey Sam and I worked with last year. And the aim was to develop a battery design tool which went all the way from materials all the way up to pack level. And this was done in collaboration with the software company Ansys Granta, and you can see the interface of the software on the slide. Then Denji Power, which is a battery manufacturer, and Rolls-Royce as potential users. So the motivation really came from looking at the diversity in the battery landscape, because as you can see here, for instance, Tesla and General Motors are adopting very different approaches to their design. You can see Tesla is quite famous for using relatively small capacity cylindrical cells, whereas Bolt is using large power cells, and that means that in a Tesla pack you'll find 4,416 cells, whereas in the Bolt you'll only be finding 288 cells. And if you look at the cell ratings, you can see that on the cell level, a cylindrical cell is achieving quite high volumetric and gravimetric energy densities. But if you look at the Bolt pack, you can see that because you can pack pouch cells more effectively, the reduction in energy densities going from cell level to pack level is lower than for a cylindrical pack. So that means that it is really important to understand why and when do you might go for the cylindrical cell and when do you go for a pouch cell, and also more generally, how do you go about comparing and evaluating the different designs on the market? Because as shown on this slide, the designs are quite different. And just so you get a flavour for the relevance, so if we break down the pack design into just a few subsystems like the positive and negative electrode, cell capacity and form factor on the cell level, and then on the pack level look at different thermal management systems and pack materials, we can simply by combining these subsystems make more than 15,000 designs. So this means that the battery design space is fairly large, and having a tool to navigate these choices is really highly relevant. So in this project we focus on pack design since our users are not producing cells but building packs, and what they need to is being able to compare different commercial cells by evaluating how they're going to perform in the final pack configuration. And the aim is to get rid of this fairly linear design process where you start by selecting a cell and then you go about choosing pack configuration, defining operating conditions, and instead being able to evaluate how your cell is going to perform in the final pack performance in an iterative way. And that's really important because some of these decisions you made in the very early design stages are crucial to final performance, but you have little or no knowledge about the final product. And the danger is that you lock yourself into an undesired design trajectory where you have to compensate later on in the process, like oversizing your system or requiring a very expensive cooling system. However, if you're using this tool, you'll be able to quickly evaluate how your choice of cell or your choice of TMS is going to affect final performance. So central to this tool was to develop a single framework where we could link design and operational conditions and strategies to final performance. And the figures of merits of performance we've selected are the ones you see in the middle. And central to this, or the foundation of this, are power and energy, volumetric and gravimetric energy densities. And then around it you see the key design parameters we have identified, and those are grouped in different groups, like the cell parameters, which have been specified in a way where we will only need data we can find on a data sheet, and that means we can actually use commercial cells. And then the rest of them have to do with how you go about designing your pack. So are you designing for end of life ratings or beginning of life ratings? And also which thermal management system are you going to use? So having all these in a single framework, we can choose different cells and also put them in different pack configurations, and then that will allow us to see how they perform in each of these different figures of merits. So the next few slides will show you how this tool works and how we go about rating our battery design. On this slide, you can see the power and energy relationship of two cells. The problem here is that we are only given 2 points, which is found on a data sheet. And that is not really going to tell you how your battery actually is going to perform under different conditions. So what we did here was to develop a power and energy relationship of a cell based on the information you can find on a data sheet. And what you see here is that all the points along these lines represents a single discharge at the specified power level and how much energy you'll be able to access in that discharge. And you can clearly see a trade-off which is completely fundamental to all lithium-ion batteries. And it shows you that only at low current or low power levels will you be able to access all of the energy inside the cell. And this fundamental trade-off is very important to understand when designing and rating your pack level performance. And another problem here is that all the lost energy is converted into heat. So the dotted lines are the lines you saw before with no temperature limit. But if you are imposing a temperature limit, you will be able to access even less energy simply because you have to stop discharging it when your cell reaches a certain temperature, in this case 55 Celsius degrees. And that is why we want to build a thermal management system around our cells so that we can achieve all the energy without violating any temperature constraints. So in order to assess how a cell is going to perform when integrated into a pack, we developed some relationship between the cell design, the pack design, and what the final performance would be when operated in a certain way. And coupled to the cell model I showed you previously, they provide the basis for the next couple of power and energy relationships I'll show you. So these relationships show you how you go about selecting your thermal management system for a specified cell. And for this cell, you can see that if you are operating at low current, there's no need for thermal management system. In fact, if you were using a thermal management system, that would take up space, so you would achieve a lower energy density and a lower power density. But as you start discharging your battery at higher rates, you will benefit from a thermal management system because you will be able to complete your discharge without violating any temperature limits. And we can also compare the different thermal management systems. So this is only for the volumetric energy density, which means that the liquid thermal management system is always going to win because it's more compact compared to free and forced air. But if we look at the gravimetric energy density, the story would be different. And the way to think about this is to identify what we call a critical current. So if we look at the graph to the right, what you see is how much energy can you access at a certain power level per cell. And what you can see here is that if you are discharging at a C rate higher than 1, it does make sense to implement some thermal management system around your cell. However, the critical current is highly sensitive to operating conditions, especially your ambient temperature. So these two plots show you the relationship between the ambient temperature, the critical current at which you have to implement the most simple thermal management system using unforced air convection, and then how that is going to affect how much energy you can access per volume. So if you look at the plot to the left, you see the cells used in a Nissan Leaf car. And what you can see here is that if you are operating a battery in hot climates where temperatures will exceed, let's say 40 Celsius degrees, you cannot discharge or charge a battery at C rates higher than 0.2 before violating temperature constraints, so you will have to implement a thermal management system. However, if you are operating at temperatures below 30, you can discharge a battery at high rates, in this case 2C, without having to implement any thermal management system. We can also compare the two plots and see how the critical current as a function of ambient temperature also really depends on how your cell has been designed. So on the left hand side we have a quite large surface, which means that we can quite effectively cool down the cell. However, on the right hand side, the cell is having a lower surface to volume ratio, which means that surface cooling is less effective. So another thing to consider when selecting a cell in your thermal management system is to look at your target cycle life. So these two plots shows you the energy you can access as a function of how you're operating your battery. And the baseline is the mustard color region, where you're not imposing any significant constraints on your battery, whereas the blue region is where you're imposing constraints to prolong your cycle life. And what we can see here is that the critical current is much lower if you are going to cycle your battery in a way that increases its cycle life. So this is effectively showing you that if you are looking to maximize cycle life, in this case by having a target temperature of 25 instead of 35, and also reducing the maximum temperature and restricting state of charge, you will have to implement a thermal management system even at low currents. So to sum up, Mat2Bat is a battery design tool to be used in the early design stages. And what it does is that it allows you to compare the performance of different commercial cells in different pack configurations, given a certain operational strategy and operating conditions. And because all of this is in a single framework, you'll be able to compare the trade-offs between different design objectives, such as designing for high energy density, designing for high power densities, or how designing for long cycle life, like restricting state of charge or restricting the temperature, is going to affect other objectives like energy or power. So with that, I'll say thank you for listening, and I'll be happy to take any questions in the Q&A session.